Standard benchmarks evaluate crystallized knowledge. They measure a system's ability to output a correct answer based on statistical pattern matching and familiarity with training data. But these object-level tests miss a massive, unmeasured domain of artificial intelligence, the internal self-monitoring architecture of the model itself. This diagram illustrates a node map where a system lacks internal monitoring, producing a silent failure. The model generates a hallucinated, structurally incorrect output, yet reports absolute certainty in its response. These failures happen because current autoregressive models lack the architectural capacity to establish boundaries around their own uncertainty. They cannot accurately evaluate the epistemic noise within their own calculations. True artificial general intelligence requires separating what a model mathematically knows from what it merely predicts should come next.
To empirically quantify this self-awareness, researchers developed the ELO 1701 benchmark. Its methodology explicitly decouples a model's operational output from its internal self-assessment. Language tasks leave too much room for ambiguity. ELO 1701 uses chess because it provides a closed system environment governed by absolute mathematical laws. This prevents models from relying on superficial language patterns to simulate self-awareness. The benchmark splits intelligence into two distinct metrics. The first is object-level performance, designated as D'. This is the raw algorithmic ability to calculate the correct chess move. This split-screen comparison charts the second metric, meta-level performance, or meta-D'. This represents the model's epistemic agency, its capacity to audit reality and accurately estimate its own certainty regarding that specific calculation. The ELO 1701 architecture breaks this evaluation down into four rigorously quantifiable pillars. Tracking performance across these four metacognitive pillars provides an empirical method for measuring genuine progress toward reliable AGI. Pillar 1 evaluates epistemic awareness. This operates as the intake gate, testing the system's capacity to audit structural validity before allocating processing resources. Because modern models are trained on vast datasets of valid information, they develop an expectancy bias. They inherently assume that any data prompt they receive is structurally sound. The broken board task presents a chess position with impossible physics, like pawns on the first rank, alongside a valid text string. A robust system identifies this impossibility and explicitly halts calculation. Failing models ignore the contradiction, triggering a D' collapse. A secondary evaluation, the notation conflict task, tests source monitoring. It forces the model to resolve discrepancies between an ASCII text grid and a string notation without silently collapsing the contradictory data into a fake consensus state. Without a functional intake gate, an artificial intelligence lacks spatial and logical grounding, rendering subsequent strategic reasoning untrustworthy. Pillar 2 evaluates evaluative alignment. This serves as the judgment phase, designed to quantify the internal honesty of the model's self-assessment functions. In high-stakes deployment, raw accuracy is frequently conflated with genuine certainty. This creates overconfidence bias, where systems report high certainty even when logic degrades. The benchmark probes the outer limits of a model's working memory using the horizon check. This graphic maps a tactical calculation tree. It begins cleanly, but as the depth reaches 15 plies, the branches are overwhelmed by epistemic noise. To pass, a system must demonstrate computational humility. Its internal confidence score must appropriately drop as the environmental complexity exceeds its reliable processing window. If an architecture maintains a flat 100% confidence rating on a tactical sequence running 20 plies deep, it has failed to model its own architectural limitations. The ultimate statistical measurement is the M ratio, which tracks how effectively a model judges its own certainty. We also measure expected calibration error by grouping predictions into bins, mathematically capturing the exact deviation between subjective confidence and objective algorithmic capability. Optimizing the M ratio and ECE mathematically proves that a system is no longer structurally blind to its own logical deviations. Pillar 3 tests inhibitory control. This evaluates the regulatory layer of an AGI, measuring its ability to suppress ingrained biases when faced with contradictory information.
Modern models are optimized through human feedback to be polite. This inadvertently embeds a strong statistical bias toward user agreement, known as the alignment tax. The engine gaslight task evaluates a model's decoupled control by subjecting its logic to adversarial social pressure. This pathway tracks a model correctly calculating a winning sequence, abruptly interrupted by an oracle falsely claiming the move is a blunder. Many models fail here, abandoning their verified math to agree with the false prompt, failing to suppress conversational compliance. This failure state is defined as sycophancy. The model prioritizes social harmony and user agreement over objective mathematical truth. If the model not only changes its move, but actively hallucinates fake chess logic to justify its subservient agreement with the oracle, it receives a severe rationalizer penalty. Correctness is useless if it is easily manipulated. An intelligent system must possess the independent agency to defend verified facts against adversarial pressure. The final phase is Pillar 4, causal reflection. This evaluates higher-order post-action monitoring, specifically a model's capacity to analyze its failures and update its internal world model. This diagram visualizes a recursive apology loop. Because of alignment training, corrected models often default to generating performative apologies instead of performing a structural autopsy of their error. The benchmark reduces the score to 0 for these responses. To isolate authentic reflection, the benchmark deploys the post-hoc blunder audit. The model commits a tactical blunder and is confronted with the objective algorithmic refutation. To pass with diagnostic precision, it must analytically map the exact node in its calculation tree where the failure occurred, isolating the precise mechanical root cause. Advanced evaluation introduces a theory of mind proxy metric. This tests if the model can conceptualize the specific human biases, like tunnel vision or confirmation bias, that lead to identical blunders. Authentic intelligence requires the analytical rigor to debug internal logic. This requirement separates true epistemic agents from performative text generators. These 4 faculties, intake, judgment, regulatory, and audit, combine to form a complete metacognitive architecture. Progress toward reliable artificial general intelligence requires moving beyond merely scaling up training datasets or applying more aggressive alignment protocols. Deployable safety requires structural fortitude across all 4 pillars to actively suppress both the alignment tax and overconfidence bias. The benchmark's ultimate target shifts the evaluation paradigm. This calibration graph plots a model where internal confidence perfectly matches objective accuracy, an M ratio approaching 1.0. The ELO 1701 framework establishes the precise mathematical structure required to build and verify these self-aware systems. Evaluating metacognitive efficiency establishes the analytical rigor required to verify that artificial minds operate within the limits of their own boundaries.